Next bit, I actually covered the exact same question in the, well, not the exact, but similar kind of question in the other component, which is the paper 2-1 component in the October-November 18 as well. This question is also highly related to what I said earlier in this question, where I talk about the electronic configuration. Tells you 2 bits of information. It tells you about the group number that is based on the number of valence electron, and tells you about the period, because depending on what shell you find the outermost shell electrons in. Okay, if these outermost electron are found in shell number 4, that means there is first, second, and third shell that are completely filled. That's why the valence electron has to fill shell number 4. So that has to do with period. All right. So those two are the 2 important information that govern the position. Well, that you can tell from a periodic table, but really they are looking for what are the factors that determine the position of an element. Okay, so what happened across when you fill in the periodic table, right? Okay, when you fill in the periodic table, what do you notice? Okay, what do you notice? The elements increase in consecutive means like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They just continue one after the other. Consecutive number of protons. The number of protons is also known as atomic number. Okay, what else? There's one thing, but then you also as we fill across the same period, we get more electrons filling in the same outermost, you can say outermost or valence shell. Okay, based on group number. So group 1 will have 1 valence electron, group 2 will have 2 valence electrons, and so on and so on. Okay, once an electronic shell is fully occupied, then we move on to fill the next shell further away from the nucleus. Further from the nucleus. Okay, so there's basically the idea of period there, and there was the idea of a group there. So it's basically describing what the periodic table is all about, really, how it comes about, yeah? Okay, so how when it was first discovered, why are the elements placed in such and such order, okay? So next bit, phosphorus is an element in group 5, U1 phosphite ion. So here you can think about phosphorus. Phosphorus was 2, 8, so it's the third period, right? It's third period element because your first period was hydrogen, helium. Your second period was lithium all the way to neon. And then your third period was, well, sodium all the way to argon. And phosphorus is somewhere in between. Phosphorus is also a group 5 element. So there's 1, 2, 3. The valence electron are in the third shell. And you have 5 valence electron because you're in group 5, all right? When you get P3 minus, you gain 3 electrons from the atoms, so it's 2, 8, 8. That is the electronic configuration of argon. That's why it gains the argon noble gas configuration, right? Next bit, you can think about this molecule. This is probably the easiest to think about it. That's ammonia, Nh3. It has 3 single nitrogen H covalent bonds. Alright, what's important, however, this is a display formula. We don't show the electrons, but each of these lines represents 2 electrons. Is a covalent bond, so one of it comes from hydrogen, one of it comes from nitrogen. They share the electrons equally. But nitrogen is in group 15, just above phosphorus. Okay, sorry, group 5, just above phosphorus. So it's got 5 outer shell electrons. It has used 1, 2, 3 for sharing, for forming covalent bonds here. So that also means 5 minus 3 used for bonding. You still have 2 more. Okay, so you can appreciate that phosphine, which is pH3, is going to look like that. Also in group 5, also like that. So now I'm going to convert this display diagram into dot and cross, where I show all the outer shell electrons. For hydrogen, it's easy because hydrogen only has one outer shell electron, which it is already used for forming covalent bond. You will not be so lucky if these are chlorine, or bromine or iodine, because then they will have other electrons, just like this phosphorus will have other electrons that are not used for bonding, that you need to consider. Okay, from my line diagram, meaning display formula, I know this is 2 electrons, but it's not just 2 cross, it's 1 cross and 1 dot, because it's 2 electrons, one from hydrogen, one from phosphorus. If I use cross for phosphorus, just like I have done there, then this would be immediately obvious, where I have 5 cross, because 5 outer shell electrons around phosphorus, only 1 dot from each hydrogen. Okay, so because that's all the outer shell electron it has. Some people really likes the shell. I do not care whether I have shells or not, because the shells are just a physical manifestation of the idea. In reality, it is not a physical thing. You don't have a physical thing that you can touch. All right, the shell is just the region of space where the electrons are always continuously moving. All right, but I mean, if you like the shell, you can draw the outer shell. It's really up to you. Yeah. Okay, I just find that drawing from display formula, and then I can get a dot and cross very easily and very quickly as well. Anyway, next bit. So they give you some properties of phosphine. Tell you it's a gas at room temperature, insoluble in water, that can react with HCl. So hydrogen chloride is HCl. So HCl is acidic. So that means the pH3, which is the phosphine, okay, because they told you pH3 is phosphine there, is going to be basic. Okay, has no, maybe not, because has no effect on litmus paper. If no effect on litmus paper, then maybe I shouldn't say anything about it. Decomposes to form hydrogen and phosphorus when you warm gently. Okay, so now you want ammonia. How are they different? But they just want 2 ways. All right. So the most common mistake I would say is people will say ammonia is liquid at room temperature, and that is wrong. Okay, that is very, very wrong. Okay, what you use in the lab is called aqueous ammonia. Aqueous ammonia is a mixture. It is not pure. It is NH3 plus water. NH3 dissolved in water. Okay, so in reality, if you do Haber process, you will know that NH3 is a gas at room temperature and pressure, which you condense down, and then you collect as a liquid in the pressure reactor. Okay, you should know that from your Haber process. Yeah, so in terms of gas at room temperature, it's not different. Almost insoluble in water. So this is the opposite of what we see from ammonia. So ammonia is highly soluble in water. In fact, that is what you use. Yeah, so you use aqueous ammonia. Example, aqueous ammonia used in qualitative analysis, all your paper 3. Yeah, but pH3 insoluble in water. Well, almost insoluble, but I'll just write that. So difference, right? Different. Next bit. So NH3 will turn litmus. NH3 will also react with hydrogen chloride. Yeah. In case you don't know, this is under your diffusion topic. All right. They like to ask this under diffusion, and then you need to think about the molecular mass of this, which one is lighter, which one is heavier, and both of these are colorless gases, and once they form this is a white solid. So I'm sure you have done this in diffusion topic as well. Yeah, but the next bit is probably one thing you can tell straight away. NH3 turns damp. In case you don't know, you need to damp. DAMP refers to you need to wet your red litmus paper a little bit wet with water, otherwise it might not turn color readily. Yeah, so it's alkaline will turn red litmus paper blue, but pH3 has no effect. pH3 has no effect on litmus. That's what it says there. All right. The other thing really is, NH3 does not decompose. Yeah, so you can have another option as an alternative really. So NH3 doesn't decompose to give you hydrogen and nitrogen when you warm it. That's why when you warm when you warm this solution of NH4 plus OH minus, you actually get NH3 plus H2O, right? This is the test for ammonium ion in paper 3, as you would know it in your theory paper as well, of course, all right? But it doesn't decompose to give you nitrogen and hydrogen, but pH3 decompose to give you hydrogen and phosphorus when you apply a little bit of warm. Remember, this is actually done by heating the test tube or the boiling tube on a Bunsen burner, yeah? Okay, I'm sure you've done this in your practical class. Now, thermal decomposition of phosphine, it says that pH3 decomposes to give you H2 plus phosphorus, all right? So you need to balance this equation. The most common mistake really is you just don't balance it in all level. There's a big mistake. Every single chemical equation you write has to be balanced, yeah? One phosphorus. The formula was given here if you read the question. This information here, hydrogen exists as a molecule, okay, at room temperature and pressure. Phosphorus exists just as phosphorus, just like that. Not entirely true, but in all level that is all right. Okay, so the phosphorus is balanced. Now you want 3 hydrogen atoms. Here is where it gets a bit tricky. You can do 3 over 2. 3 over 2 times 2 is 3. So how many hydrogen atoms do you have on the right? 3 over 2 times 2 is 3. Some people really don't like fractions. You can multiply the whole thing by 2. You're going to get 2, 3, 2. Perfectly fine with me. If you're happy, I'm happy, provided it's balanced, yeah? Next bit. Describe and explain the difference in the rate of diffusion of the gases. So here is not ammonia plus HCl, but it's ammonia and phosphine. But the same idea of a diffusion applies. Is to do with the relative molecular mass, yeah? So you can work out the MR of NH3, which is 14 plus 3 is 17. And then the MR of pH3 is 31 plus 3, which is 34. So what I can say is pH3 is heavier than NH3. Therefore, pH3 diffuses slower than NH3. You might not have done pH3 in your syllabus, but you know, same example which you have come across. So chemistry is all about relating ideas, yeah? So the ideas never change, okay? If you have the ideas, no one can take that away from you, unless you are just memorizing facts which might not make sense on its own, okay? Next bit, phosphorus 5 oxide. So they're asking whether it's acidic, basic, or amphoteric. You should know that phosphorus 5 oxide is acidic. Okay, it can dissolve in water. To form acid. Okay, or I guess in all level you can say it's a non-metal oxide. Therefore it is acidic. Non-metal oxide like oxide of nitrogen, oxides of sulfur, you know, sulfur dioxide, sulfur trioxide, nitrogen dioxide, nitrogen oxide. So those are all acidic oxides. So they can dissolve in water, in rainwater, can cause acid rain, right? Okay, but I'll show you just this equation. I don't think you're necessarily expected in all level. So phosphorus 5 oxide is phosphorus plus 5, oxygen minus 2. This is actually a simple molecule, but because they give you the oxidation number, what you can do is you can get P2O5 just by working out the LCM between the two, and you need 2 of these and 5 of these, okay, to balance the formula based on the oxidation number. I'll show you what is the acid being formed. The acid that you get is actually H3PO4. This is also PO4 3 minus because it's H plus. You can think about 3 of them. So in this case, your phosphorus plus 4 times minus 2 is minus 3. So your phosphorus is actually plus 5 as well. Okay, when you dissolve the oxide in water, you are not doing redox. Okay, phosphorus is in group 5. It has 5 outer shell electrons. It doesn't go to plus 6 because the maximum it wants to do is it just can afford to lose 5 electrons. Okay, to lose 6 electrons would mean to lose the noble gas configuration anyway, yeah? Okay, so any equation you write has to be balanced, so you can get 2 phosphorus, so 2 phosphorus. Hydrogen, there's 6, so should have a 3 in front. And then in terms of the oxygen, there's 3, and 5, there's 8. So 4 times 2 is 8. So this equation is balanced automatically. I don't necessarily think you need to know this equation at all level, but these are probably what you need to know. Okay, to relate it to oxide of nitrogen, oxides of sulfur, which are acidic oxide and can cause acid rain.